So, welcome to this session. So, in this session we will discuss about Maxwell's equations which are related to the magnetostatics. So, till now we discussed about different equations or different phenomena which are related to the electrostatics. Now, we will go for magnetostatics. And so, what is electrostatics and what is magnetostatics? Once again we will rewind. Electrostatics, a static charge will be there, the charge will be at rest, and magnetostatics, the current what we are considering to generate some magnetic field is steady. That is nothing but it is not time varying. Already just we will in brief we will discuss so what is magnetic field and how current and magnetic field will be related. Just let us consider, we are considering a conductor. So, whenever there is a conductor and some current is flowing through the conductor, then a magnetic field will be generated around that conductor. That how the magnetic field will be generated and what is the direction of that magnetic field. To observe that, just we need to consider a right hand thumb rule. That let us take, this is the direction of current what we are considering, the thumb direction is the direction of current and the folded fingers direction is the magnetic field direction. So, let us take this is the current once again, this is the conductor whatever we are considering, that if the current is flowing in this direction, then the magnetic field will be generated around that conductor in this particular direction. In the same way, if the current is flowing downwards, then the magnetic field will be generated in this particular direction. With this simple basic concept, what we do is we will go for few important parameters which are related, few important laws which are related to our Maxwell's equations. Since the Maxwell's equations are very important for understanding our wave propagation phenomena, we need to observe how these Maxwell's equations were derived. Before that, just recollect what are the Maxwell's equations we got in our electrostatics. In our electrostatics, we got two important equations. They are del dot D is equals to rho V. This equation was derived for using our Gauss law. And del cross E is equals to 0, this is the equation what we derived from the concept of potential. So, right, these two are written in our simple as a point form or differential form. Now, in the same way what we have to do is we have to derive two more equations that which are related to our magnetostatics. So, in brief we will discuss what are the laws which are related to the two more equations of our Maxwell which are in our magnetostatics. This is the first law what we are supposed to discuss in magnetostatics, that is also called as Gauss law for magnetostatics. Just here we must require a basic practical phenomena. So, what happens if a magnet is divided into two pieces? Let us consider a bar magnet we have. That this is a bar magnet what we have, it's not only bar magnet, for any type of magnet. So, let us take a bar magnet and every magnet, it's from the general observation we can say that every magnet will have a north pole and south pole. And if you cut into two pieces, let us take just two pieces of the same magnet, that what I am doing is I am cutting that one into two pieces, then what happens? Clearly we can observe a practical phenomena that each piece will have once again a north pole and south pole. That this magnet will be once again will be divided as a north pole, south pole. This part what we are considering will be divided as a north pole and south pole. Once again, if you cut into two pieces, or that the entire system was made into four pieces, then you can observe north pole, south pole, north pole, south pole. It's a combination of north pole and south pole for each and every piece. So, from that general observation, what we can say is a single pole, so that is nothing but the monopole for a magnet, it does not exist. So, clearly remember this point, whenever we are considering a magnet, monopole does not exist, but the electrostatics will have monopoles, that a single positive charge will be there, a single negative charge will be there, or combination of some negative and positive charges will be there, that is called as a dipole. But in magnetostatics or in detail, for any magnet, we do not find a single north pole, we do not find a single south pole. So, whatever may be the body we are considering, definitely a north pole and south pole combination will be there, and in general, so both are in same magnitude. So, what I can say is the net charge for the magnet what we are considering is 0. So, the total charge or the net charge on any magnetic body, in any magnetic body, is always equals to 0. Just keep this point in your brain and just now come to your Gauss law for magnetostatics. How the Gauss law for electrostatics was defined? The total flux leaving through any closed surface is equals to the charge enclosed, right? The same concept we will apply to our magnetostatics also. The total magnetic flux leaving through any surface, that is nothing but the closed surface, is equals to the total magnetic charge enclosed within that particular surface. For that, what I do is I will consider a magnetic body. Let us take, this is a magnetic body what I am considering. Around that magnetic body I will form a gauge surface. It's a closed surface that what I form, and I will calculate total magnetic flux which is leaving through the Gaussian surface. Once again, for the calculation of the total flux which is leaving, we require flux density. Here this is a new term what we are going to learn, that the flux density, it's a magnetic flux density, was denoted with a symbol capital B. This is also a vector. This capital B is a magnetic flux density. The units are Weber per meter square. Later I will give you the comparison between the magnetic fields and electric fields. For time being, remember that this B is a vector, it's a magnetic flux density. It's represented in Weber per meter square, and the magnetic flux will be represented as phi. This is our magnetic flux and the units are Weber. Now what we are supposed to observe, the total flux which is leaving through the Gaussian surface for the magnetic body what we are considering, we are supposed to observe. That must be equals to the total magnetic charge which is enclosed within that particular surface. So let us take, this will consist of a equal amount of negative at north and south poles. Then the total charge enclosed within this one is obviously 0. That what we learned just now, right? Now we have to calculate the total flux leaving. The total flux leaving is nothing but your phi. The total flux leaving can be calculated from its flux density B. So how these two can be related? The relation is same as your electrostatics relation. So no difference in this. So the total flux leaving can be calculated using its total flux density B with the relation phi is equals to integral B ds, right? So here what I do is, I will relate them. So the total flux is equals to, for the closed surface what we are calculating, we are supposed to integrate this B. So for a closed surface B ds, which is nothing but the total charge enclosed, that is the magnetic charge enclosed, is 0. So surface integral of B ds is equals to 0. This is the important equation what we are supposed to remember, and that will be called as the integral form of Gauss law for magnetostatics. So very simple equation that which describes non-existence of magnetic monopole. The magnetic monopole does not exist. That simply surface integral of B ds is equals to 0. Now apply our divergence theorem. So since we have a closed surface, we can apply the divergence theorem here. By applying the divergence theorem, what we will get here, it's a surface integral now becomes a volume integral. Surface integral is a double integral, volume integral is a triple folded integral. So volume integral of the divergence of B dV is equals to 0. Just what I am doing is, I am applying divergence theorem here. So volume integral of divergence of B dV here, and from the observation clearly we can say that del dot B is equals to 0. So this is called as Maxwell's equation for magnetostatics, one of the Maxwell's equations for magnetostatics in its point form or differential form. This is the equation in integral form, this is the equation in point form. Just interpret that equation. Del dot B is equals to 0, divergence of magnetic flux density is 0. So magnetic flux density is not diverging. Not diverging means how much amount of flux is leaving, the same amount of flux density is entering to the same body. That clearly what you can say is, the magnetic flux or the flux density which is leaving from the body will reaches the same body again. But this phenomena will not be observed in our electrostatics. If some flux is leaving through the electric charge what we have, that may reach another electric charge. So if it is leaving from the positive charge, it may reach negative charge. But here what we can observe is, some flux is leaving through this north pole that may reach south pole which has on the same body. That clearly the magnetic monopole does not exist. This is what we have to remember from our Gauss's law. Now we have to go for another law, it is called as Ampere's law, for the observation of our fourth Maxwell's equation. Now we will discuss about Ampere's law, which is one of the important law. We are supposed to observe for magnetostatics. What Ampere defined? So Ampere defined the relation between the magnetomotive force and the total current enclosed within a closed loop. The statement of our Ampere's law is like that. It's a very simple. The total magnetomotive force around a closed loop is equals to the current enclosed within that particular loop. So here what we have to do is, you have to observe the total magnetomotive force as well as the total current enclosed. Just if you observe, it resembles our Gauss law. The total flux leaving is equals to the charge enclosed. The same way, the total magnetomotive force is equals to the current enclosed. Now the interpretation will be like this. Consider a closed loop. So this is a closed loop that what we have. We are supposed to calculate the total magnetomotive force. How the magnetomotive force can be calculated? Simply with its magnetic field. So let us consider the magnetic field H is here. This H is a new parameter that what we learned just now. This H is called as the magnetic field intensity. This magnetic field intensity will be described in terms of current per meter, that is ampere per meter are the units. So in the earlier we discussed about magnetic flux and magnetic flux density. Now we discussed about this magnetic field intensity also. So what is the relation between this magnetic flux density and magnetic field intensity? Magnetic flux density B is equals to permeability of the medium into magnetic field intensity mu H. Just it resembles the equation D is equals to epsilon E. Here also it is B is equals to mu H. So we will discuss a little bit about this later. Now consider the magnetic field intensity is there. Using this magnetic field intensity we can calculate the total magnetomotive force which is observed, which can be observed along the closed loop. Now that magnetomotive force is equals to the current enclosed within that particular loop. So then consider the current which is enclosed within that particular loop only, don't consider the current which is outside the loop. So what I do is I will consider the current which is enclosed by this loop. Let us consider this is the current which is enclosed by this loop, that I will take that one as I. So from our Ampere's law, it's clearly the total magnetomotive force which are calculated, which is being calculated for the loop is equals to the current enclosed. So if you write that one as an equation, the total magnetomotive force along the closed loop, that is along the closed loop, the magnetomotive force is HDL, which is equals to the total current enclosed. So which is simply I enclosed. But we don't know what is the current which is enclosed in that one. For that what we are supposed to do is we are supposed to take the current density for this particular cross-sectional area which is formed by the closed loop. Now integrate that current density with respect to the surface what we have, then we will get the total current. So what I do is I will consider a cross-sectional differential surface ds and J as the current density already we learned. So I will integrate this J with respect to this ds, then what I will get is the total current enclosed within this closed surface, right? That's closed surface within this surface formed by the closed line. Now this total I enclosed can be written as the surface integral of J ds. That's what I am writing. Just I am writing the equivalent of this current enclosed. Then so just observe here what we have is a closed line integral, here what we have is open surface integral. So clearly these two can be related with our divergence theorem. It's not divergence theorem, Stokes theorem. So simply a Stokes theorem will be useful for equating these two. So apply Stokes theorem to the left-handed side term. So closed line integral can be always converted as open surface integral by considering curl of this particular vector H, that is surface integral of del cross H ds is equals to, on the right hand side same I am writing, that is J ds. Now just you rearrange this equation, a surface integral of del cross H minus J ds is equals to 0. So here what we are doing is we are considering some arbitrary surface, a random surface, that what we are considering. For any random surface, if this particular term is equals to 0, then from the observation clearly we can say that the integrand del cross H minus J is equals to 0. Del cross H minus J is equals to 0 corresponds to del cross H is equals to J. This is the fourth equation what we are supposed to remember as Maxwell's equations in its point form. Then what is the integral form? The first definition what we have, this is the integral form. A line integral of HDL is equals to I enclosed, which is the integral form of Maxwell's equations for static fields, and del cross H is equals to J. This is the point form or differential form for the Maxwell's equation in magnetostatics. That till now we discussed or we derived 4 equations. The interpretation will be taken later. We derived 4 equations, 2 are related to the electrostatics and 2 more are related to the magnetostatics. At a glance, just I will give you what are those 4 equations. Now I will write the 4 Maxwell's equations what we derived in their point form it is very easy to remember if you remember those equations in point form. Later we can convert them into the integral form whenever it is required. And I will give you shortest form, how to convert the integral form to the differential form to the integral form. So before that, just at a glance, I will give you those 4 equations. These are the 4 Maxwell's equations purely which are meant for static fields. That whenever we are considering a charge which is at rest, electrostatic equations will comes into the picture. Whenever we are considering a steady current, that is, it is not time varying, our magnetostatic equations will comes into the picture. The first equation was derived from Gauss's law. As we discussed the Gauss's law in electrostatics, this equation is the result that what we have, that del dot D is equals to rho V, the diverging electric flux is equals to the total volume charge, that what we have. The second one, del cross E is equals to 0, that the electric field is irrotational for static fields. That's once again, always this static fields condition is very, very important. For del cross E is equals to 0 is only for static fields, and del dot B is equals to 0. The magnetic flux density is not diverging, it is 0 diverging field. And the final equation, del cross H is equals to J. So what I mean by del cross H is equals to J? So whenever we have a curling magnetic field at any point, the current density can be observed. So clearly, a rotating magnetic field, if we have a current density can be observed. These 4 equations were compiled by Maxwell, and he want to relate these equations for time varying fields. So these are all static fields. You want to relate these equations for time varying fields. But what he observed is these 2 equations, that what we have, that del dot D is equals to rho V and del dot B is equals to 0, are satisfying the time varying equations also, time varying fields also. But the equations which are related to the curl, that is del cross E is equals to 0 and del cross H is equals to J, these 2 are not suitable for time varying fields, that what he observed. For that, what he did is he manipulated those 2 equations using 2 more laws or some other phenomena. That how he modified, and what is the interpretation of those time varying fields, now we will discuss. After discussing all those time varying equations, once again we will compile. So what are time varying fields, Maxwell's equations, how to convert them into the static fields, and how they will be interpreted for different conditions. So now what we do is, how these 2 equations, that is del cross E is equals to 0 and del cross H is equals to J, were modified by the Maxwell, we will observe. So for that, we must learn 2 more laws, that is a Faraday's law, that which is useful for manipulation of these equations, and another one is inconsistency in Ampere's law was removed by introducing a simple term called as displacement current by Maxwell. So these 2 we are supposed to learn. We will start that one with Faraday's law. What is Faraday's law? How Faraday defined or related different phenomena, different parameters what we have. Just simply the statement is very simple, just we need to remember like this. The total electromotive force what we have around a closed loop is equal to the rate of change of magnetic flux, and the direction of the rate of change of magnetic flux opposes the original flux what we have. This is a very simple statement. Once again, the total electromotive force around a closed loop is equal to the rate of change of magnetic flux, and the direction is opposite to the original flux that what we have. For this, how to consider this one, and what are different conditions? Let us take a closed loop is there. In that closed loop, we are calculating the total electromotive force. The total electromotive force can be calculated using electric field intensity. For that, what we are doing is we are assuming that the electric field intensity is applied here. Since we are applying electric field intensity, the electromotive force can be observed. That electromotive force generates a magnetic field or magnetic flux density. That magnetic flux density opposes the original magnetic flux density what we have. So here different parameters we are supposed to correlate. So simply what I do is I will try to observe what will be the electromotive force EMF which can be observed in this particular closed loop, and how it relates to the magnetic flux what we have. Let us take the magnetic flux what we have is phi. So as per our Faraday's law, it is also called as a Faraday's law of electromotive force, EMF, right? So clearly the total electromotive force along the closed line is EDL, the total electromotive force along the closed line is equals to the rate of change of magnetic flux. The rate of change of magnetic flux is d by dt of phi, but it opposes the original flux what we have. Since it opposes, this negative sign is very, very important. We are supposed to put before that dou by dou t term. So here clearly the total EMF what we are calculating, this term is nothing but the EMF, which is equals to the rate of change of magnetic flux and which opposes the original magnetic flux. This is a very simple Faraday's law, but it is very much useful in understanding our radiation phenomena. That our Maxwell took this equation and he modified this equation. How he modified this and how he utilized this? Just observe here. So line integral of EDL is equals to minus d by dt of phi. So this phi can be calculated using its magnetic flux density. Let us consider magnetic flux density B is there. For the cross-sectional area, let us consider the magnetic flux density. So this phi and B can be related using its simple relation surface integral of BDS. So I can replace this phi with surface integral of BDS. So this entire term will give us the total magnetic flux. So the electromotive force line integral of EDL is equals to minus d by dt of surface integral of BDS. Now clearly observe, the integration is with respect to the spatial coordinates and the differentiation is with respect to the time. So here clearly we can swap these two operators. If we swap, this d by dt operator can be applied to what? That what we are supposed to observe. That this d by dt operator can be applied on B, or this d by dt operator can be applied on S also, right? So when it will be applied on B, when it will be applied on DS. So if clearly observe, if B is time varying, we can apply the dou by dou t operator on B. B is time varying means it is time varying field, and S is static, that is not varying. That is one condition we are supposed to remember. Or if S is time varying, we can apply this d by dt operator on S also, and B can be kept constant. Or this B and DS both are time varying, so we can apply that d by dt operator on that B dot ds. So here clearly we are supposed to observe three cases. That the case 1, B is varying with respect to time, S is fixed. Second case, S is ds is varying with respect to time, B is fixed. Third case, so both are varying with respect to time. So if you observe all these three, what happens to them? If B is a function of time, that what I am saying, and ds is fixed. B is a function of time means clearly what you can say is the loop what I am considering is kept constant at some location, that it is fixed, and the magnetic field what we are observing or applying is time varying. So it is varying with respect to time. So simply it is called as transformer case. So transformer EMF. The EMF was induced because of transformer action. That clearly observe, in the transformer what we have is a fixed coils. In the fixed coil, the magnetic field what we are generating or applying was time varying. So the magnetic field is time varying, ds is not at all varying, then simply this action is said to be transformer EMF. So simply it is transformer action. The second case what we are supposed to observe is B is fixed, the magnetic field is static. Static means it is not varying with respect to time, and ds is a function of time. So ds is a function of time. What do you mean by ds is function of time? The cross sectional area what we are considering is varying with respect to time. So imagine like this, just we are taking a loop and we are rotating it. See, in a fixed magnetic field we are rotating the loop. So for every second the loop area, cross sectional area was changing. So this particular phenomenon is called as generator phenomena, generator action. So generator action means the magnetic field, for the applied magnetic field, continuously we are rotating the loop. For that, with the cut-in flux we can generate the electromotive force. That electromotive force is nothing but the potential. Just you observe this one, this is called as potential. So a potential can be generated in this one, right? So this one is called as generator principle. And the third one, so both magnetic field is varying with respect to time and the cross sectional area is also varying with respect to time. So it is a combined action of these two, that is B is a function of time and ds is also a function of time. So this is a combined of 1 and 2. That what we can write. So here clearly these three are the three cases what we can observe using our Faraday's law. But clearly remember, we don't require these three cases, just we require the first case. Since we are discussing about the time varying fields, the fields are time varying, this is the case that what we are supposed to take. So by considering the transformer EMF, we will try to get the very beautiful equation which is used to get radiation equations. So what I do is, I will take this time varying field with fixed loop and I will try to modify this equation. Yes, consider this equation. Now as we discussed, there's a transformer EMF is the case that we are supposed to take here, that B is time varying, ds is fixed. So that what I do is, I will apply this d by dt term to the B, then the right hand side term will now becomes, it's clearly a surface integral, a surface integral of minus dou B by dou T dot ds. Just clearly remember why I am applying this dou by dou T term to B is because of only the transformer action, that we are considering time varying fields, the field must be time varying, right? So it is a surface integral of minus dou B by dou T ds. So once again we have a closed line integral and a surface integral. Whenever we have these two can be related with the Stokes theorem. So apply Stokes theorem to the left hand side term. So if you apply Stokes theorem to the left hand side term, this equation now becomes a open surface integral of del cross E ds. So del cross E ds is equals to surface integral of minus dou B by dou T ds. Now for any arbitrary surface, that what we have, clearly we can say that del cross E is equals to minus dou B by dou T. So what is the interpretation of this equation? And so remembering this equation in differential form or point form is very easy, and we can interpret that equation in an easiest way. Del cross E, so del cross E is nothing but, so rotational nature of E we are observing, right, which is equals to minus dou B by dou T. So it is existing means the E has a rotational nature, that clearly E has rotational nature. When you come to the time varying field, the phenomena was changed. In the static fields, del cross E is equals to 0, it has no rotational nature. It is starting at positive charge, ending at negative charge. But when you come to the time varying fields, it has no starting point and ending point, that it has rotational nature. Say rotating electric field, that what we are observing. So how this can be generated, how this can be observed, with rate of change of magnetic field. That if you replace that B with mu h or mu naught h for free space, then simply we can say that we are observing the rate of change of magnetic field. So whenever we have, so the interpretation will be like this, whenever we have a rate of change of magnetic field with respect to the time, then you can observe the electric field, and the electric field is clearly rotating. That what we can observe. So this equation is very important, and this is said to be the modification for the equation what we learnt earlier and was derived by our Maxwell. So this is simple modification, that what we need to remember, del cross E is equals to minus dou B by dou T. So one more equation is there, that is del cross H is equals to J. That del cross H is equals to J also was modified by our Maxwell. Now we will observe how it was modified. To observe that one, we need to go for once again Ampere's law. The del cross H is equals to J is derived from Ampere's law, right? So that Ampere's law describes a relation between the current density and magnetic field intensity. But Maxwell found that there is some inconsistency in the Ampere's law. Whenever we are coming to the time varying fields, that this inconsistency plus very important also, he identified that inconsistency and he eliminated that. So what is the inconsistency in Ampere's law? Just observe, what is our Ampere's law? Del cross H is equals to J, where J is conduction current density, which is equals to sigma E, right? Del cross H is equals to J, this is our Ampere's law. What Maxwell did is he applied divergence on both sides. Just apply divergence on both sides, that is divergence of curl of H is equals to del dot J. Now clearly observe, divergence of curl of any vector is always equals to 0. So the left hand side term now becomes 0, which is equals to del dot J. Now clearly observe the right hand side term, that is del dot J we are observing. For which one we are observing? For the time varying fields we are observing. For the time varying fields, let us take some charges conserved. Since there is some charge, definitely we can observe some field and etc. right? So for a time varying field, if you are observing it for a conserved charge, then what about this del dot j? Already we learned our continuity equation. In the continuity equation, we learned this del dot j is equals to minus dou rho v by dou t. So whenever the current is diverging, which is equals to reduction in the charge with respect to the time, the rate of change of charge density with respect to time, and it is getting reduced, right? So whenever we are applying this one to the time varying field, definitely this will satisfy. So the continuity equation must be satisfied for time varying fields, and if it is conservative, right? Now observe here, what we got is del dot j is equals to 0, but what we have for our time varying fields, del dot j is equals to minus dou rho v by dou t. So clearly this 0 is not equals to minus dou rho v by dou t, that what Maxwell's observed. So if you take the continuity equation, del dot j is existing, and if you take the equivalent of this one, this del dot j is getting vanished. So what this one is called as a simple conflict in the Ampere's law, that what we have. So what Maxwell did is he tried to eliminate that conflict, that it is called as the inconsistency in the Ampere's law. For that what he did is he added some other term. How this some other term will be added? He derived that term from this continuity equation. How that term will be derived? Just observe here. The continuity equation is del dot j is equals to minus dou rho v by dou t. From the Gauss law, this rho v can be replaced with minus dou by dou t of del dot d. Already we know this del dot d is equals to rho v from the Gauss law, del dot d is equals to rho v. We can replace this one, right? So now swap these two operators. This is a time domain operator, this is a spatial domain operator. So swap these two operators, then what we get is del dot minus dou d by dou t. Now bring this one to the left hand side. Del dot j plus del dot dou d by dou t is equals to 0. So just what I did is I brought this one to the left hand side. Now apply volume integral on both sides. That what I do is I will apply volume integral on both sides. Then a volume integral of del dot j plus del dot dou d by dou t dv is equals to 0. On the right hand side, just what we have is just 0. Now this is clearly related to our divergence theorem. So this volume integral can be converted to the closed surface integral. That this can be written as a closed surface integral of j plus dou d by dou t ds is equals to 0. Just observe what we are calculating here. We are calculating some parameter with respect to a closed surface, and we are getting that must be equals to 0. Now he took this equation and he analyzed what is this new parameter. So this is the new parameter which is added to this JDS. It's a JDS always a current, right? So this J plus dou d by dou t, that what we got is also must be current. So what is this dou d by dou t? We are adding this one to the current density. So this dou d by dou t also must be current density. He named that current density as displacement current density. So Maxwell named this particular dou d by dou t term as displacement current density or flux current density. Now clearly observe the current density. What we are observing is not only the conduction current density, it is displacement current density also. Now the Ampere's law statement will be modified a little bit like this for our time varying fields. So what is the basic statement of our Ampere's law? The total magnetomotive force is equals to the current enclosed. That's the same statement, but here the current enclosed is what? The current enclosed is because of the conduction current density as well as displacement current density. So if you want to write the statement for our Ampere's law in time varying fields, the total magnetomotive force around a closed loop is equals to the total current enclosed. That current is a contribution of, clearly the extension is important, that current is the contribution of both conduction current density as well as displacement current density. So what he did is he took our basic Ampere's law and instead of the current density J, he replaced that J plus dou d by dou t. So simply the equation will be modified like this. In its differential form, del cross H is equals to, initially it is just simply current density, that what we are considering. Now that current density is the summation of displacement as well as conduction current densities. So del cross H is equals to J plus dou d by dou t, that what we are supposed to write. And clearly remember, this dou d by dou t term must be added whenever there is some time varying field. So for time varying field, this dou d by dou t will be added and it is called as displacement current density. The units are same as our conduction current density. It also has ampere per meter square. So this is a very simple equation which are supposed to remember as a fourth Maxwell's equation in its differential form. Now I will write this one in its integral form also. So after compilation. So clearly observe here, the differential form of this Ampere's law will be obtained after the modification that what Maxwell did. So clearly we are supposed to remember this modification. So just with this one we derived 4 Maxwell's equations for both static fields as well as time varying fields. What I do is I will take the time varying field equations and one by one I will try to compile them and I will try to analyze them. So what is the basic form and how to interpret this one, how to convert them into different forms. Now what I do is I will take the time varying fields Maxwell's equations and I will try to modify them as per our requirement. Here we are supposed to take them in different domains and different forms under different conditions. So what I do is basically I will give you the 4 Maxwell's equations which are meant for time varying fields, and in a simplest way I will try to give you the modification for those equations. So one by one I will write those 4 equations. Just observe, and always what I suggest you is remember these 4 equations only. Don't go for any integral form, don't go for static fields, don't go for any other conditions. Just what you are supposed to do is you are supposed to remember these 4 equations as the basic equations which are meant for time varying fields, right? Now I will try to write them in their integral form. So all they are mentioned in point form and I will try to write them in integral form. Before that, just let me give you, so when the integral form will be applied, when the point form will be applied. So the name itself indicating point form, whenever you have a particular point, if the medium is discrete medium, then you are supposed to, so point means at a particular point, whenever you have a point, you are supposed to apply this differential or point form. And the medium is a continuous medium, then you are supposed to go for the integral form, right? And whenever there is a discontinuity, you are not supposed to observe differential form. So because at the discontinuity, differential form is not suitable. It's not at all applied. So clearly remember, for a continuous medium, we are supposed to apply integral form, and for a continuous medium, you are supposed to apply differential form. For a discontinuous medium, you are supposed to apply integral form. Remember that. Discontinuity, integral. So continuity, differential. At a particular point, differential. So what I suggest you is just you remember these differential form of equations. I will try to give you how to convert them into integral form. First you observe. So what are different operations here? Del dot means a divergence operation is there. So divergence theorem is applied here. Just remember like that. Del dot, divergence and divergence theorem is applied. Del dot, divergence theorem was applied. Next, del cross, curl, Stokes theorem was applied. Del cross, curl, Stokes theorem was applied. And blindly remember, whenever you have differential form, just on both sides apply volume integral. To convert this one into our integral form, both sides apply volume integral. Here both sides apply surface integral. So divergence form, volume integral, curl form, surface integral. So just observe what I am doing here. Just I have applied the volume integral on both sides, right? For this particular equation, I have applied the volume integral. Next, observe the left hand side term. For the left hand side term, clearly you can observe which is related to the divergence theorem. Since a volume integral divergence we are calculating, that can be related to a closed surface integral. Recollect that one. So clearly the left hand side term can be converted as a closed surface integral. So this equation now can be written as a closed surface integral of just it is d ds. And what is the right hand side term? Volume integral of rho v dv. Volume integral of rho v dv is nothing but the total charge enclosed, that is q enclosed. Don't go for any other simplification, just that is the integral form. That once again simply observe what I am doing. I am taking the differential form, and remember 2 points. Whenever there is divergence, apply volume integral. Whenever there is a curl, apply surface integral. So apply volume integral. So I have applied volume integral on both sides. Then this is the modified equation. Simply this is said to be the integral form of this differential equation. Right. Next, observe the second equation. Here what we have is cross product, curl. Since we have cross product, Stokes theorem comes into the picture. For that, the simplified way, apply surface integral on both sides. That what I am doing is I am applying surface integral on both sides. That is del cross E ds, which is equals to the surface integral of minus dou b by dou t ds. Nothing I did except application of our surface integral. Now once again just clearly observe, this is the term which is related to the Stokes theorem. So left hand side term can be simplified using our inverse of the Stokes theorem, that this can be simplified as a closed line integral of E dl. So clearly the left hand side term can be written as a line integral of E dl, and which is a closed line. And the right hand side term can be written as minus d by dt surface integral of b ds. That is the integral form of our differential equation. So once again clearly observe what I am doing, that whenever you have a curl, apply Stokes theorem on that one. That apply surface integral on both sides, so that the simplified equation what we get is the integral form of this equation. In the same way, try to simplify the third equation, del dot b is equals to 0. Since we have del dot b, that the divergence we have, apply volume integral on both sides. Volume integral, that, so volume integral of del dot b dv is equals to, on right hand side, volume integral 0, which corresponds to the left hand side term. It's a volume integral of divergence, that simply is a divergence theorem. So a closed surface integral comes into the picture. That is a closed surface integral of b ds is equals to 0. So simply this is the integral form of our Maxwell's equation. That's the third Maxwell's equation. Now in the same way, try to simplify this equation also. Curl we are getting. Since we are getting curl, Stokes theorem comes into the picture. So apply surface integral on both sides. That surface integral of left hand side term, that is del cross h ds, which is equals to, on the right hand side, the same surface integral we are supposed to observe, s plus dou d by dou t ds. Now once again clearly observe, on the left hand side what we have is surface integral of curl. Surface integral of curl can be converted into the closed line integral. So using our Stokes theorem, simply the left hand side term can be written as a closed line integral of h dl, which is equals to, on the right hand side just a simple modification, that is surface integral of j ds plus d by dt of a surface integral of d ds. That what we can write. So this is called as integral form of our last equation. So just once again observe what I am doing. I am taking the differential form, and using this differential form, so once again I am saying don't remember these equations. Using the differential form, try to derive them. So by applying our divergence theorem and Stokes theorem, if you derive them easily, you can observe the differential form of the equations as well as integral form of the equations. And here one more important point is that you are supposed to remember which equation is related to which law. So the equation 1 is related to what? Clearly that is from Gauss law. So if you remember the statement, we can say that del dot d is equals to rho v, or surface integral of d ds is equals to the total charge enclosed, which is nothing but simply Gauss law. For electrostatics, that is also very important. This is Gauss law for electrostatics. And a similar equation what we have, that is del dot b is equals to 0 in its differential form, and surface integral of b ds is equals to 0. This is also called as Gauss law. but is for magnetostatics. So remember this equation as Gauss law for magnetostatics. So here what we have is a Gauss law. One is for electrostatics, another one is for magnetostatics. Next, you may get confusion among Faraday's law and Ampere's law. But don't get confused. Just remember the word inconsistency in Ampere's law. Inconsistency in Ampere's law. So there is something which is problem in our Ampere's law. That's why another term was added. So whenever there is an added term, remember that one as an Ampere's law. If you are unable to remember the statement of Ampere's law which relates our magnetomotive force and etc. etc. So just what you do is remember at least this word inconsistency in Ampere's law. That's why another term was added. That del cross H is equals to J plus dou d by dou t is the term which was added. Since a new term was added, clearly you can say that which may be related to our Ampere's law, and that is our Ampere's law, that what we are supposed to remember. And the last equation what left for us is Faraday's law. So this equation came from our Faraday's law. So remember this equation as Faraday's law. So just observe. So these are the basic equations what we are supposed to remember. Later we will modify these equations. Just observe what we have is del dot d is equals to rho v, surface integral of dd is equals to q enclosed related to the Gauss law. The same equation, surface integral of bds is equals to 0, del dot b is equals to 0 related to our Gauss law, which is related for magnetostatics. The same law was also called as non-existence of magnetic monopole. Since the magnetic monopole does not exist, so this equation is satisfying. So in the examination, the statement may be of any type. Just remember like that also. And this equation came from Ampere's law. That Ampere's law was modified by the Maxwell to eliminate its inconsistency by adding this term. So J plus dou d by dou t, whenever you find this J plus dou d by dou t, that Ampere's law comes into the picture. And del cross E is equals to minus dou b by dou t, or line integral of ED is equals to minus dou by dou t of BDS. This is called as Faraday's law. Now clearly observe for your understanding and easy remembering. Once again I will say, the electric field intensity what we have here is related to the magnetic flux density. So electric field intensity, magnetic flux density were related. In the same way, magnetic field intensity and electric flux density were related. So clearly remember, these two equations are very very important equations which are supposed to observe for radiation. That whenever you have electric field intensity, magnetic field intensity can be observed. Whenever you have magnetic field intensity, electric flux density can be observed. So for confusion, he may give instead of B, he may give D here, and instead of D, he may give B here in the examination. Don't get confused. Electric field and magnetic field will be related. Magnetic field and electric field will be related. So these four equations are the base equations. Now what I do is just I will try to convert these time varying fields to the static fields. Already we learned those static fields, but for our convenience what I do is I will try to give you so how these equations will be modified both in differential form as well as in integral form. Now consider the time varying field equations only. Now I will try to modify these equations as per our requirement. Now here what are the fields we are considering? Static fields. The charge is at rest and the current what we are considering is steady state current, steady current, right? So whenever we are considering static fields, clearly remember, blindly remember, there will be no time varying term. That whenever you find the time varying term, make it equals to 0, right? Here you can observe different time varying terms are there. Here dou by dou t, this is a time varying term that what we have. Here also dou by dou t, time varying term we have. So make them equals to 0 for static fields. So just observe the first one. The first one will be modified. Del dot d is equals to rho v. There is no time varying term here. So as it is equation, we are supposed to write that del dot d is equals to rho v. This is the equation what we are supposed to remember for static fields also. There is no change in this equation. Come to the second equation. Del cross E is equals to minus dou b by dou t. Clearly you can find a time varying term here. Since we are observing for static fields, make it equals to 0. So what is the equation we will get? Del cross E is equals to 0. So this is the equation what we derived for our static fields. If you remember, this is the equation that what we have for static fields. And the third one, that is del dot B is equals to 0. Here also there is no time varying term. Since there is no time varying term, as it is equation we are supposed to write, that is del dot B is equals to 0. The third equation will be unaltered. And fourth equation, in the fourth equation what we have is a time varying term, make it equals to 0 for static fields. If you make it equals to 0, then the equation what we have is del cross H is equals to J. Once again clearly remember, these four equations already we derived, the names will be unaltered, that this is Gauss law, electrostatics, gas law, magnetostatics, and this is our simply Faraday's law, and this is our Ampere's law, with any modification, without any modification, right? In the same way, if you write our integral form of equations, in the integral form of equations what we have here, surface integral of dds is equals to q enclosed. Do you find any time varying term there? So no. So simply this equation will be unaltered. So don't change any term in this equation. This is said to be the integral form of our Gauss law for static fields. We come to the second equation. Line integral of ed is equals to minus dou by dou t of bts. But here clearly you can observe a time varying term. Since we have a time varying term, make it equals to 0. So simply what I am doing is I am making it equals to 0, that this term will be vanished for static fields. That a line integral of EDL is equals to 0. That what we are supposed to remember as integral form of our Maxwell's equations for static fields. The third one, surface integral of BDS is equals to 0. Since there is no time varying term, leave it as it is. So this is the equation what we are supposed to remember, and it is unaltered. And the fourth equation, line integral of HDS is equals to surface integral of JDS plus d by dt of surface integral of DDS. Here clearly observe, this d by dt term is there. Since we are considering it for static fields, the dou by dou t term becomes now 0, and this equation will be modified as just a surface integral of JDS. So what do you mean by surface integral of JDS? The total current enclosed. So this can be written as just I enclosed. A line integral of HDS is equals to I enclosed. This is the integral form of our Maxwell's fourth equation. So just now we observed how to convert the integral form of Maxwell's equations which are written for time varying fields into the static fields. So this is a simple modification we are supposed to remember. Now what I do is I will try to modify these equations into the phasor form. Till now all they are written in their original forms. Now what I do is I will try to write those equations in phasor form.